Swayam Prabha. Digital India. Educated India.
Welcome to lecture 5. Today I will be going through some more properties of ideals. So last time I have defined what is an ideal, and then I have shown you how to construct ideals in a ring, and then we were trying to characterize how does the ideals in a field look like. So today we will try to understand how does the ideals in the ring of integers or in the ring of polynomial ring over a field looks like. So let's start with the ring of integers and try to understand how does an ideal in that ring look like. So for example, so let me start with this ring of integers. So let us consider the ring Z, and then we will be trying to understand how does the ideals of this ring Z look like. So we will see that every ideal in Z is generated by a single element. Every ideal in Z is generated by a single element, and it is of the form nz for some n in Z. That means every ideal in the ring of integers is nothing but a multiple of this any integer n. So let us see how does the proof goes. So if you look into the proof, so we know from the definition of ideal that ideal has to be a subgroup with respect to addition, and from the group theory you already know that the subgroups of Z are of the form nz. Therefore, if it has to be an ideal, then it has to be of the form nz. So since an ideal is a subgroup with respect to addition, and any subgroup of Z is of the form nz, so therefore the possible candidate for the ideal will be nz. And we can see that if I take all the multiples of n and if I multiply anything from the ring of integers, then again it will be multiple of n. So it is closed under the operation from the elements of the ring. Therefore, in fact nz is an ideal. So the ideal of Z are of the form nz. So we have identified all the ideals in the polynomial ring, in the ring of integers a, z, which are nothing but multiple of some integer. Now let us try to understand what is happening in the polynomial ring over a field. So if I go to the polynomial ring over a field, so let f k be a field and Kx is a polynomial ring, then and Kx be the polynomial ring over K, that means the coefficients are coming from this field K, then every ideal in Kx is again generated by a single element which is known as principal ideal. Then every ideal of Kx is principal. So, this is the fact that I will be proving next. So, how do you prove that every ideal of Kx is generated by a single element? So, let us start with a proper ideal which is not the 0 ideal and not the whole ring, because we know the 0 ideal and the whole ring are generated by respectively the 0 element and the multiplicative identity. So, they are in fact principal ideals. So, let us start with, let I be an ideal. So, let I be an ideal such that I is a proper ideal, that means it is not the 0 ideal and not the whole ring. So, then in I there will be at least one polynomial of positive degree. So, then there exists a polynomial of positive degree in I. So, I will try to show that I will be generated by a single element, that means I have to find out an element which will generate I. So, how do I choose that element? So, what I am doing, that I am considering that fx is the polynomial in I with the smallest positive degree. So, let fx belongs to I is a polynomial having the smallest positive degree. So, then I would like to show that this ideal I will be generated by this polynomial fx. So, next I would like to show that I will be generated by this polynomial which is of smallest degree present in I, okay, will be generated by this fx. So, let us see. So, of course, any multiple of fx will be in the ideal because fx is in I, but let me choose any arbitrary element from this ideal I and try to show that it is a multiple of fx. So, let us start with any arbitrary element gx in I, and what we will do now. So, degree of gx will be greater than equal to the degree of fx, then I will apply the division algorithm, and then what I will get. So, let gx be any element in I, and by division algorithm I can write down, by division algorithm we can write down that gx is nothing but fx into some qx plus rx. What is this rx? Rx is known as the remainder, and this rx I have, so this where this either degree of rx is strictly less than degree of fx or rx is equal to 0. This is what we know from the division algorithm. Now, from here you can see that this Rx can be written as Gx minus Fx into Qx, where I know that this Gx and Fx both are in the ideal I, therefore, their difference will be in the ideal I. So, this implies that this remainder term Rx is also in the ideal I. But the degree of Rx is strictly less than degree of Fx, and Fx was the element with the smallest positive degree possible in I. That means Rx should not have a positive degree, which is not possible. That means that which leads to a contradiction to the fact that the degree of Fx is the smallest one. So, by minimality condition, so by minimality of degree of fx, we can say that this Rx belongs to, this Rx is in fact is equal to 0. This implies what? This implies that here you can see that I have this Gx I have written in this way, where now this Rx is 0 means this Gx is nothing but multiple of Fx. Therefore, this Gx belongs to the ideal generated by Fx. So, therefore, this implies that this Gx belongs to the ideal generated by Fx. Therefore, we are done. So, we have started with any arbitrary element Gx in I, and we have shown that this Gx is nothing but a multiple of Fx. That means, it is in the principal ideal generated by Fx. Therefore, I am able to prove that I will be nothing but the ideal generated by Fx. So, with this I am able to show that every ideal in the polynomial ring over a field is generated by a single element. This is very important, that I am the hypothesis that this is true only in a polynomial ring over a field. But if I suppose just change this polynomial ring over any arbitrary ring, then it need not be true anymore. So, let me give you one example for that. So, the example, for example, if I consider the polynomial ring over Z, so Zx. So, in general, I have so far only talked about polynomial ring over a field, but the same thing you can define for any arbitrary ring. So, let me just say it as a remark first, and then maybe I will go to the example. So, I will come back to this later. So, let me just first go to the example. So, let me first write the remark, sorry. So, remark is that, so let R be any ring, then I can talk about the ring Rx. What is Rx? Then Rx is nothing but the polynomial ring. Then Rx denote the polynomial ring in indeterminate x with coefficients in R. So, this Rx is also has a ring structure. It is exactly the same. The addition is like the component wise addition, and the multiplication is also defined in the same way. But here one thing you need to observe, that this Rx will be commutative if your ring, the coefficient ring is commutative. So, here note that Rx is a ring with the addition and multiplication defined previously, but Rx will be commutative if the ring R is commutative. So, this is one of the very important observation, that in general not any arbitrary polynomial ring is commutative, but if I consider the polynomial ring over a commutative ring, then the polynomial ring will be commutative. And in general, we can talk about the polynomial ring over any arbitrary ring, that need not be have to be a field. So, keeping this in mind, I will now give you the example. So, the example that I am going to give is the following. So, consider the ring ZX . So, Zx means what? This is the polynomial ring over the ring of integers. Here the coefficients I am considering from the ring of integers, not from any field. Okay. So, now here you can see, if I would like to show that here not every ideal is generated by a single element. So, consider the ideals. So, here not every ideal of Zx is principal. So, how do I show that? So, let us consider the ideal I, which is generated by 2 and x. Now, I would like to show that this ideal cannot be generated by a single polynomial. So, suppose that I can be generated by a single polynomial fx, where fx is a polynomial in Zx. Now, I would like to get some contradiction. So, now what happens that if I is generated by a single element fx and this is same as the ideal generated by 2 and x, that means this 2 belongs to the ideal generated by fx. So, since 2 belongs to the ideal generated by fx, that means that 2 can be written as a multiple of f. So, 2 can be written as fx into gx for some gx in Zx. So, that means which polynomial can divide 2? I know that the only divisors of 2 are nothing but plus minus 1 and plus minus 2. Therefore, the possible candidate f will be either plus minus 1 or plus minus 2. So, therefore, this implies that, so since here you observe that degree of 2 is 0 and no 2 positive degree polynomial can get multiplied to a 0 degree polynomial, this implies that degree of f has to be equal to 0, and also I am having that f divides 2. So, this implies that f has to be equal to either plus minus 2 or plus minus 1. So, now f cannot be equal to plus minus 1 because then it will be the whole ring. So, in that case I is a proper ideal I have started with. So, therefore, f has to be equal to either plus 2 or minus 2. So, since the ideal generated by 1 and minus 1 is nothing but the whole ring and I is not the whole ring, therefore, f has to be equal to either plus 2 or minus 2. But if f is equal to plus 2 or minus 2, then there is a problem because x belongs to the ideal generated by fx. So, in that case what will happen, that x is in the ideal generated by fx. This implies that x can be written as fx into Lx for some Lx in Zx. But there is a problem now because fx can be either plus 2 or minus 2, but none of 2 or minus 2 divides x, but 2 does not divide x. Therefore, this x does not belongs to the ideal generated by 2 or minus 2. Hence, what I can say is that this ideal cannot be generated by a single element. Therefore, the ideal generated by 2 x cannot be generated by a single element. But then what is happening if I consider the same ideal instead of Zx in Rx? So, let us see that. But consider the ideal 2, x in Rx. I know that Rx is a polynomial ring over a field and there every ideal is principal ideal. Therefore, this 2, x, this ideal should be also generated by a single element. But what will be this ideal generated by 2, x? You can see now that 2 is an unit element because 2 is a real number now we are treating as, and it has a multiplicative inverse. So, since 2 is an unit element in Rx, therefore, the ideal generated by 2 and x will be nothing but the unit ideal, which is nothing but the whole ring. Therefore, you can see that it is very important that over which ring I am considering the ideal. The same ideal when I am considering over Zx, it is not the unit ideal. In fact, it cannot be generated by a single element, whereas the same ideal if I consider in Rx polynomial ring over a field, then it becomes the unit ideal which is generated by the multiplicative identity. So, this was all about identifying the ideals of polynomial ring over a field and ring of integers. Now, I would like to say about some operations that we can do over ideals. So, for example, if I take two ideals and take their sum, whether their sum is an ideal or not, or we can talk about the product of two ideal or not, intersection of two ideal, is it an ideal, union of two ideals, is it an ideal or not. So, all these things now I am going to do next. So, let us start. So, let me first define what do I mean by addition of two ideals. So, let I and j be two ideals of the same ring R. Okay. Then the sum of these two ideal I and j is defined as, how do I define the sum? So, I plus j, I am defining it to be all the elements of the form A plus B such that A is coming from the ideal I and B is coming from the ideal j. So, you can look that since I and j both are subgroups, so these I plus j, these also have a subgroup structure, and I and j both are closed under multiplication. So, if you consider their sum and multiply by some element, it will be again of the form I plus j. So, therefore, I plus j is in fact an ideal, and this is the smallest ideal. So, this is the smallest ideal containing I and j. This is the smallest ideal containing I and j, because if I consider here the element 0 from j, and then it will give me the ideal I, and on the other hand if I consider A to be 0, then it will give you the ideal j. So, I plus j in fact is the smallest ideal which contains both I and j. Now, I will define the product. So, how do I define the product? So, the product of two ideal ij is defined as the finite sum of the form ai into bj, sorry, ai into bi I is varying from 1 to n, where ai is in I, bi is in j, and n is a positive integer. N is a positive integer. So, this is nothing but the collection of all finite sums of the form ai bi. So, where ai is coming from I and bi is coming from j. So, here you can note that if I just consider the elements of the form, so note that if I consider the set just AB where A is in I and B is in J, then this is not forming an ideal because it is not closed under addition, that means it is not forming a subgroup. So, therefore, we need to define the product of two ideal in the above mentioned way. So, note that this set AB consisting of just the product of elements from I and J is in general not an ideal. Because if you go by the definition of addition, then you can see that we have just added the elements from I and j and constructed I plus j. So, it will be natural that you take the product, one is coming from I and another one is from j, and then that might be an the product ideal, but it is not like that, because this product is not in general an ideal, because this is not an ideal as it is not closed under addition. That is why I have to define the product in the above mentioned way. Now, I can talk about, I have addition, I have product, then I can talk about the intersection also. So, I intersection j, if I consider, then you can check that it is also an ideal. It is in fact a ideal which is sitting inside I as well as sitting inside j. So, this is an ideal, and there is some relation between this intersection and this product. So, if you look carefully, then you can observe that this product Ij, where it is the finite sum of the form summation of ai bi. So, here you can see that ai is coming from I and bi is coming from j. Therefore, their product is in I as well as in j, and of course, it is closed under addition, therefore, it will be in both. So, that means Ij is already sitting inside I intersection j, but you can ask whether this is equal or not. Most of the time it is not equal. So, this containment can be strict. I will give you an example to show that this containment is in fact a strict containment. So, let me go to that example. So, suppose the simplest example, I consider my ring to be the ring of integers z, and I am considering my ideal I and j to be the same ideal, say 2z, then what will be your I intersection j? So, I and j both are the same ideal, so I intersection j is nothing but 2z only. But what is your ij? So, if you look into the definition of ij, so this is the product of the form some element is coming from I into some element coming from j. So, that means it is multiple with 2, so it will be multiple of 4. So, this ij is nothing but the ideal 4z. So, here you can see that I have this containment is strict, that means 4z is strictly sitting inside 2z. That is, in this case Ij is strictly contained inside I intersection j. And you can, so let me tell you when it will be equal. So, just as a remark, You can verify this also by yourself, this is not difficult. So, if I and j are such that there, if I add this 2, then this is nothing but the whole ring. That means I plus j is the whole ring. In that case, I have that this product is same as the intersection. So, under this condition, we have that when the addition of two ideal is the whole ring, in that case their product and intersection are the same thing. So, I will stop here with this properties of ideal, and these are the references that I have used for this lecture, and thank you.